So quiz one starts off with finding the difference quotient. I think a lot of you guys were a little iffy on this problem, really dealing with some composition of functions here. And the importance of parentheses, I would say, is very crucial for a question like this. So we're simply finding what our f of x plus h minus f of x all over h is in simplified form using the function that they gave us, x squared minus 4. So how do we go about doing this? Well, this is our f of x, so we can actually just take this whole guy and put it into our f of x. However, our f of x plus h is slightly modified, which means wherever you see an x in our f of x, we're going to draw some parentheses. So we're looking at parentheses squared minus 4. And inside those parentheses, our x plus h goes. So we have x plus h. And that's essentially it. Now you're just plugging everything in and simplifying. We have our f of x plus h is this whole guy. So our x plus h in parentheses squared minus 4. And then we have our f of x, which is this guy here, minus, because it's all being subtracted, you want to use parentheses because you're distributing that negative to each term, both the x squared and the negative 4. Again, maybe color code this so you really see it. All over our h. Maybe I'll box this in green. Now we just have to simplify. So x plus h in parentheses squared simplifies to just x squared plus 2xh plus h squared. And then we have this minus 4. Then we're going to utilize our distributive property. So we get negative x squared. A negative times a negative 4 gives you a positive 4. And this is all over h. Looks a little complicated, but lucky for us, things cancel out. And in, I would say, 95% of these problems, things should always cancel out. So if they don't, then you made a mistake and you want to go back and figure out what you did wrong. X squared minus x squared cancels to 0. Negative 4 plus 4 also cancels to 0. So we're left with 2xh plus h squared over h. But you'll notice in the numerator, we can factor out an h from each term. And why is that important? Well, our denominator is h. And what's h divided by h? It's 1. 5 divided by 5 is 1. 128 divided by 128 is 1. X divided by x is 1. H divided by h is 1. So our final simplified result is just 2x plus h. Again, later on, you'll learn that this is part of our definition of a derivative. Okay. Any questions on this problem? No. Let's move to question 2, which we're asked to find the domain of this function. And again, what's the two criteria for finding domain? You want to think restrictions. And so your first one, denominator is not equal to 0. And then the second is radicals. They have to be greater than or equal to 0. Otherwise, we hit the imaginary world. So, lucky for us, we have both of these conditions here. Some of you guys just did the undefined, but if you notice in the numerator, we have that radical. So we need to take care of that as well. So let's first do the denominator. Our 3 minus x cannot be equal to 0. And so what value of x makes that undefined? Well, you just add x to both sides, and then you get x can't equal 3. So that's a restriction. Now, the second part, what's underneath that radical, the 2 plus x, needs to be greater than or equal to 0. And so what does that tell us? If we subtract 2 from both sides, then x must be greater than or equal to -2. We need to use both of these pieces of information in order to cultivate our domain. So in the first one, if we were to sketch this out on a number line, all we would do is put an open circle at 3 because we don't want to include 3. Everything else is included. Whereas that second condition, if we create a number line over here, we are going to put -2 on our number line. And in this case, it's going to be a closed circle because square root of 0 is possible. And 2 minus 2 gives us 0. And then we're shading in everything that's greater than that -2 because that is part of our solution set. So everything in pink is part of our domain. And so if we were to combine these, we would essentially get this third number line graph, but at 3, it would be an open circle because we're excluding that value. Which means if we have to put this in interval notation, what does this look like? This looks like -2, we're including that -2, all the way up to 3, but 3 is a soft parentheses because we do not want 3 in our domain. Union, another soft parentheses at 3, because everything above 3 up to infinity is also part of our domain. And that concludes this problem. Any questions on this one? Right. Let's move on to question 3, which I believe was a piecewise function. And so we're asked to sketch this piecewise and then write the domain in interval notation. So the two different functions that we're looking at are x and x plus 1. And that x value where the functions change are at 0. X and x plus 1 are both linear functions, so we're going to be dealing with lines here. And let's first start with that first one, x. So we're including 0 at this point, so we're going to have a closed circle at 0, because if we plug in 0 for x, we get 0. So 0, 0 is a closed circle. And then it's saying that everything smaller than 0 we have this slope of 1 and y-intercept of 0. So we're essentially reading it left to right, going up 1 over 1, or we're going down 1 to the left 1. So we can plot a few points and then just connect the dots. Right. First part's complete. Now let's look at the second part. Second part, it's x plus 1. And this is for all values greater than 0. We still want to figure out, okay, what is our point 1x equals 0 so that we can put an open circle there. So we plug in 0 for x and we get 0 plus 1, which is 1. So 0, comma 1, we're going to have an open circle. And then let's plot some additional points. What's our slope? X, our slope is 1, right? Because there's an imaginary 1 right in front, which is 1 over 1. So we're just essentially going up 1 over 1 a few times. And then we once again connect the dots. So this is our graph of the piecewise function. We also don't want to forget to write the function itself or labeling it. I did not take points off for this last part, but anytime you're graphing, you should always label your graphs. So moving forward, I will take points off. And lucky for you, this coordinate plane was labeled with the proper scale and XY axes. That won't always be the case. The last part of this problem is we need to identify what the domain is in interval notation. And again, when you think of domain, you have two restrictions. Denominator can't be equal to 0, and the radicals, it can't be a negative value underneath that radical. And so, do we have any restrictions here? How many people think yes? How many people think no? There's no restrictions, right? We're representing all x values in the real number system, all the way from negative infinity, shooting up and to positive infinity, which means our domain, just said it, it's negative infinity to positive infinity in interval notation. And we're done. The last part is just testing your knowledge of local max and local min values. So I'll zoom in on this question for you. And so we're given this function f. Remember, local maxes are mountain peaks or top of a hill, whereas local mins are dips. So I'm just color coding for you guys to show you that we're going to have two local maxes and two local mins in this example. And you really want to highlight it using the y value. So we have 1, this is 2, this is 3. And then the two local maxes are at 2 and at 3. So you just do 2, 3. If you did a coordinate point, I did give you credit, but you really should get into the habit of just emphasizing it from that y value. And for the pink, we have 1 at 0 and then 1 at -1. So -1, 0, and we're done. Any questions? No.